Another reason why we may want to think about modeling repeated games, about modeling repeated interactions, is because sometimes we want to model a potentially repeatable situation. And here the word potentially is important because it's not necessarily that the situation actually repeats in practice, right? So it's a potentially repeatable situation which does not necessarily repeat. Right, the important part here is just that it could repeat, that there are some future rounds, future stages of the game which could happen, and that makes players here and now, when they decide on what they want to do, that makes them take that into consideration and, act accordingly and modify their actions accordingly. So to predict what they will do now, we need to know what they could do in the future. That's just something we do to be able to accurately predict their activities. So again, an example of a game which I think we could use to inform our discussion about this kind of situations is a game of bargaining. People bargain over different things. Typically, when people bargain, what they do is that it's like several people, two or maybe more than two, have access to some value, and they bargain over the way they will divide this value between themselves. So for instance, one example of bargaining is when you bargain over price. The buyer and the seller on a market, in fact, in an actual market, for instance, somewhere in an eastern country or in a southern country, for instance, the buyer wants to buy a carpet or a rug and the seller sells it, but there is no price tag, right? So the buyer asks the seller what the price would be, and then the buyer tries to lower the price and the seller wants to keep it as high as possible. And they bargain over this well, actually they bargain over the price of the rug, and then they meet somewhere in between. Typically, that's our expectation. So what they really do is they divide between themselves this extra value of the rug. So the seller gets some extra money over his or her estimation of what this rug is actually worth, and the buyer gets another part of it which she manages to cut down from the initial stated price, right? That's an example of bargaining. In our example, and I mean there are lots of other possible examples of why and over what people bargain, but in our example, just to keep things simple, there will be two players who will be bargaining over a pie, right? And I don't mean the Greek letter, I mean an actual pie. I would even try drawing it, but I'm not very good at drawing. So they are bargaining over a pie. The way they will be bargaining is as follows. There will be just two players, and they will both get to suggest a particular way of dividing the pie between themselves. So they suggest partitions of the pie. this is what it looks like. So we'll assume that the whole pi gives them utility equal to 1, equal to unity. So if you get the whole pi, you get 1. If you get half the pi, you get half, etc. The first player who suggests her partition will call first, right? So the first player suggests some partition, and this partition is just first player's strategy in this game. So let's just say that it's S1, and it can be anything from 0 to 1. And then the second player is told what the first player proposes him, right? So the first player makes an offer saying something like, I will take this much and you take the rest. And then the second player can either accept this proposal, say yes, or reject it and say no, I don't like what you propose. If the second player says no, then it's the second player's time to propose some partition. So then the second player names some partition S2, right? And then it's the first player's time to say yes or no. If the first player says yes, then the game is over. If the first player says no, then the game is over. So let's say that if the first player says no in this situation, they both get nothing. All right. So their payoffs are 0 and 0. If the first player says yes, then the first player will get what there is left remaining of the pi after the second have taken S2 out of it, and S2 goes to the second player who was making the offer here. And the same works for the situation where it was the first proposing and the second agreeing to this part of the game. So in this part of the game, if the second player says yes, then the first player gets S1, this value that the first chose within her offer, and the second player gets 1 minus S1. That's a very simple game, and for some reason the two players are only bargaining in 2 rounds. Of course, you understand that I want them to bargain in 2 rounds because they are 2 players, so I wanted each of them to have a chance of offering their bargaining solution, their particular way of dividing the pie. And we can solve this game by using backward induction. So because that's just a usual dynamic game that we are used to, right? So to solve it by backward induction, we look in the very end of the game, and let's make an assumption. This is what our assumption will be. It's important, so I will write it in blue. We'll assume that the player who is offered as much as the player would otherwise get agrees to the offer. So player agrees to an offer which is no worse than what she would get otherwise. And she gets otherwise. That is, if she refuses, if she rejects the offer, right? So what that means in particular is that Well, have a look at this situation here in the very end. We are solving the tree. So the first is choosing between getting a 0 from saying no and getting 1 minus S2 from saying yes. And the second player in this situation, when the second player suggests this S2, has to take into account the fact that the second player so the second player has to take into account that he wants to maximize this value of S2. Second player maximizes S2, right? Because S2 is her payoff. As long as the first says yes. So the value of S2 should be the maximal value, which would still make the first player say yes rather than no. And in this situation, given the assumption that we made that the player agrees to an offer which is no worse than what she would get otherwise, here that means that the first player would choose between this 0 and this 1 minus S2. And the first player would agree to a part equal to this 1 minus S2 could be equal to 0, right? Because in this situation, comparing 0 to 1 minus S2, and according to the assumption that we made, the first player would have to say yes. And it follows from this that obviously S2 would be equal to 1, right? So the second player in this situation would say S2 equal to 1. And now we continue into the previous subgame. We know that here the first player is making her proposal as one which can be something between 0 and 1. And the second player would be inclined to say yes if the payoff she gets, this one, 1 minus S1, is no less than the payoff she would get there, and we have already solved the subgame there, so we know that there she would get S2 equal to 1. So it follows from here that 1 minus S1 should not be less, so should be greater or equal to S2 equal to 1. And that means, in turn, that S1 should be less or equal to 0, right? So in order for the first player to get a yes in this situation, she would have to say that S1 is, well, it couldn't be less than 0, right? She could not take a negative part of the pie to herself. It can only be equal to 0. So S1 would be equal to 0. And that means that now with this assumption that we made, the Nash equilibrium in this game would be as follows. The first player says offers S1 equal to 0. That's her first node here. And we know that there would be another node that the first player could play at here. And here we know that the first player would say yes. Right? So this is the full strategy for the first player. And for the second player, the full strategy is to say yes to this offer. So when the first player offers the second player the whole pie and only leaves 0 of the pie to herself, the second player says yes. However, if the game continued, somehow out of this magical head that we discussed sometime in the very beginning of the course, then she would offer a partition as 2, the part for herself, equal to 1. And that's it. That's a Nash equilibrium. Now, many of you would look at this game and say, okay, nice stuff, thank you so much. What does it teach us? That does not teach us much, and the reason is that this strange assumption that we made, if they offer you a 0 and you could get a 0, you agree to the offer. Many people would say that, that's not how the world is, right? Because if they offer you nothing, then, I don't know, out of pride, for instance, you would reject the offer. So there is this tiny element of pride. But imagine that we do two things. First, we just cancel the pride. So there is no pride. We just cancel it out from our modeling. And second thing, instead of saying that the player agrees to an offer which is no worse, we say that the player agrees to an offer which is somewhat better than what she gets otherwise. So for instance, returning to the situation where the first player agreed to a 0, imagine that instead of giving her a 0, the second player would give a tiny little piece of the pie, and the first player would know, okay, either I get this 0 from saying no, or I get this tiny piece, like 1/100th of a pie, really the smallest piece possible. And then the second player would get the rest of the pie, almost all of it except for this small tiny piece. Then, if there is no pride, the first would agree to that, right? Because having at least a little bit of the pie is still better than having none at all. And then the second player would take that into account and offer not exactly 1, but almost 1, just shy of 1, like 0.99 etc. And then the second player in the previous step would not say yes unless here at this stage would not say yes unless the first offered her this 0.99 of the pie. So on the first move, the first player would take S1, which is almost equal to 0. Just a little bit more than a 0, exactly what she would get here. And then the second player would get S2, which would be almost equal to 1, right? Well, it would be 1 minus this almost 0 that she would get that the first player decided to take for herself, right? So if we relax this assumption, if we change it a little bit, then you see the result is almost the same, of course, unless you factor in the pride into the game, which we will not be doing here. The interesting development of this game is, of course, introducing more rounds into it, and also something which we will be calling the discount factor.